Welcome to qnawire.
In this problem, we're asked to determine the velocity of the mass center, G, of the panel after the ball's or the sphere's impact. So, in the first part of the sketch, so you can see here that a sphere with a mass or with the weight Ws is dropped from a total height of 18 inches. So, to a panel that is initially at rest. So, at point C, labeled in the diagram. So, giving it a speed of Vc1. So, the impact caused an impulsive reaction. So, look at the second part of the diagram with force F at point A. Also, upon impact, the sphere now has a velocity Vc2. So, and the panel, this causes the panel to rotate with angular velocity omega about point A. Hence, the mass center G is now moving or now moves at a velocity Vg. So, before we start with writing the equations, let's first make some conversions and initial calculation of some quantities. So notice that our dimensions here are in inches, but we actually need them in feet. So let's convert inches to feet. So 7 inches times the conversion factor, 1 foot times 12 inches. So this is equivalent to 7/12 foot. And then we have 9 inches. So 9 inches times 1 foot over 12 inches. So this gives us 9/12 foot. And then lastly, 18 inches times the conversion factor, 1 foot over 12 inches. So this is equal to 18/12 feet. And then, notice that we're given the weight of the sphere and the panel, but we actually need their masses. So solving for the mass of the sphere, so we have m sub s or ms equals the weight of the sphere over the acceleration due to gravity. So that's 4 pounds divided by 32.2 feet per second squared. So this is equal to 0.124 pound second squared per feet. And then for the mass of the panel, square panel, so weight of the panel divided by acceleration due to gravity. So that's 16 pounds divided by 32.2 feet per second squared. So this gives us 0.497 pound second squared per feet. Now, for the moment of inertia, so based on the shape of the panel, so the equation for its moment of inertia would be 1/6 times the mass of the panel times the length of the side squared. So in our case, this would be 1/6 times the mass, so 0.497 pound second squared per feet times the square of the side, which is 18/12 feet. So this will give us 0.186 slug feet second. And then lastly, we can also calculate for the velocity Vci of the sphere before impact. So since it's dropped from a total height of 18/12 feet, so the velocity Vc1 is equal to, so since it was dropped, so there's no initial velocity, so our equation would be square root of 2gy, or the height from which it was dropped. So this will be, so 2 times 32.2 feet per second squared times the height, which is 18.12 feet. So this will give us 9.83 feet per second. So these are our values. Now, so since Vg and Vc2 are linear velocities, so we could come up with an equation for them. So we can express them in terms of r, or the radius or distance from the rotation point, and the angular velocity or omega. Hence, Vg is equal to, so since G is 9 inches away from point A, so that would be 9/12 foot times omega. So this will be our equation 1. And then for Vc2, so in our illustration, so notice that Vc2 is the distance between A and point C. So the segment AC is equal to, so notice that this is a diagonal or a hypotenuse of a right triangle, AC, the segment AC. So its length, so VC2 before that is equal to AC omega 2. So this AC is again the hypotenuse of a right triangle with sides 7/12 foot and 9/12 foot. Okay, so to calculate, let's first calculate the length of AC. So this would be, so 7/12 foot squared plus 9/12 foot squared, then square root. So this would give us 0.950 foot. So hence Vc2 is 0.950 omega. So this is our equation 2. There. So now we'll write the equation for the moments about point A. So that's our chosen rotation point or axis, taking the clockwise direction as positive. So we'll have, our equation would be mass of the sphere times Vc1, and then C is 7/12 foot away from point A, then plus 0, equals the mass of the sphere again, so ms, then Vc2. So C here is 0.950, just like what we've computed, 0.950 feet away, then plus moment of inertia omega plus mp times Vg, then G is 9/12 foot away. Sorry, let's not write the units for simplicity. Okay, so this is our equation 3. Now, substituting the values that we have and also equations 1 and 2, so this will become, so 0.124 times Vc1, which is 9.83, then 7/12 equals again 0.124 times our equation for Vc2, which is 0.950 omega, then 0 times 0.950 plus the value of the moment of inertia, which is 0.186, then omega times omega plus 0.497 times the equation for Vg, which is 9/12 omega times another 9/12. So simplifying the equation, so the right hand side would be equal, left hand side will be equal to 0.711, and then for the right hand side will have 0.112 omega plus 0.186 omega plus 0.279 omega. So further simplifying the equation, we'll have 0.711 equals 0.577 omega. And lastly, so omega is equal to 0.711 divided by 0.577. So this is equal to 1.23 regions per second. So again, we need to solve for VG. So we will use this omega to solve for VG. So using our equation for VG, so we'll have, so VG equals, so 9/12 foot times omega. So this would be 9/12 times 1.23 regions per second. So this would be equal to 0.923 foot per second. Now, if you want to get the value in inches, because the original given values are in inches, so we can convert this to inches per second. So 0.923 foot per second times the conversion factor. So 1 foot is equal to 12 inches. So this would be equal to 11.1 inches per second.